Hi, my name is Peter Mell. I'm from the National Institute of Standards and Technology, and today I will be talking to you about our work on measurements of the most significant software security weaknesses. As background, the Common Weakness Enumeration, it's a community repository containing software flaw types. These are not vulnerabilities or instances of software flaw types, but these are the software flaw types themselves, the types of flaws in software that then will result in vulnerabilities. In 2019, the CWE community created a top 25 most dangerous software weakness list, and this data is critical. We must inform programmers and security educators on the types of software flaws that they need to avoid, those that result in tens of thousands of computer vulnerabilities every year. We need to inform the creators of software bug scanning tools so they can prioritize their efforts in finding software flaws that result in lots of vulnerabilities and vulnerabilities that are very severe for software. Now, the top 25 most dangerous CWE list used an equation called the Most Dangerous Software Errors Equation, or MDSE. It's intended to combine frequency and severity together equally. In fact, it just multiplies normalized frequency by normalized severity. And it uses the NIST National Vulnerability Database for its data collection. So to get frequency, it uses the NVD mappings of vulnerabilities to CWEs. For severity, it uses the NVD mappings of vulnerabilities to the Common Vulnerability Scoring System. Unfortunately, our work finds that the 2019 top 25 CWE list, that those results are flawed. The updated 2020 acknowledges some of those flaws, and it's improved, but it is still flawed. And in this work, we're going to discuss the problems here and how we propose to mitigate them. So let's look at the MDSE equation's inclusion of severity and frequency. So in two figures, every dot represents a CWE. The yellow dots represent CWEs that were not included in the top 25 list. The red triangles represent the CWEs that were included. On the left, notice that the normalized CVSS, it's not actually normalized from 0 to 1, but that's a smaller flaw. But note here that the red triangles show that the top 25 CWEs identified really have varying severity values, and it goes across the distribution. However, on the right side, notice that the red triangles, the top 25 CWEs, are exclusively those with the highest frequency. So really the top 25 most dangerous CWE list really is the top 25 most frequent CWE list. Now, that said, the ordering of the elements in that list is somewhat affected by severity, but the inclusion on that list is exclusively based on frequency. So looking at our mitigated equation, our MSSW, or most significant security weakness equation, and looking at its inclusion, notice on the left side that we now normalize fully between 0 and 1 on the severity scores. And notice that on the left side that we choose CWEs that tend towards being higher severity, which is what we want, but are not exclusively the highest severity ones. And on the right side, again, we include CWEs on our top list that tends towards being the higher frequency CWEs, but they're not exclusively the highest frequency CWEs. And notice on the x-axis that we use a double log of the frequency, and that's our main modification in mitigating the flaw in the MDSE equation. And we'll discuss that more in a second. So from another perspective, let's look at risk maps. So we're plotting severity versus frequency. For the MDSE equation, on the left side, notice how the CWEs really hover along the x-axis because most of the CWEs have a very low frequency compared to a few that have very, very high frequencies. On the right side, with our fixed normalization on the x-axis and using a double log of the normalized frequency on the y-axis, notice how we spread the values out, the CWEs out throughout the risk map. And that enables our MSSW equation that linearly combines frequency and severity to give them more equal footing. So, comparing the two equations, the original equation appears to balance frequency and severity equally. Again, it just multiplies normalized frequency by normalized severity. Challenge 1 is that it doesn't fully normalize the severity, but hey, that's a minor thing. Challenge 2 is just that frequency dominates because a few CWEs have very, very, very high frequencies. The frequency, follows almost like a power law distribution. In our new MSSW equation, we again multiply normalized frequency by normalized severity, but we do the double log of the normalized frequency. So why do we do that? So in the bottom right figure, it shows what's going on here. On the x-axis, we're arranging the CWEs in ascending order by frequency. And the y-axis represents the normalized modified frequency. Now, the blue line, though, represents just the raw frequencies. I mean, normalized from 0 to 1, but the raw frequencies. And you can see after about 100 how they really rapidly, shoot up in frequency value. The yellow line represents the log of the frequency values, and the red line represents the double log of the frequency values. And our goal here was to pseudo-linearize the frequency values at the high end of the range between, 90 and 120. And the double log, achieves that result to enable us to match against the severity figure that's identical, that has a more linear aspect. Okay. So now, these were not the only challenges with the MDSE equation. There were also data collection issues, where the MDSE equation doesn't propagate frequencies from children to parent CWEs. And there are parents at a high level of abstraction with children at low levels of abstraction, and this really undercounts the parent CWEs that have many and or popular children. Because the National Vulnerability Database just maps CWEs to the CWE at the lowest level of abstraction. And so NVD doesn't map to all applicable CWEs, just the lowest level of abstraction, but the MDSE equation doesn't propagate the frequencies from the children to the parents. Also, the MDSE equation includes all the CWEs together, irrespective of their level of abstraction. So it includes the high-level pillars and classes with the low-level, variants. For example, it's mixing apples and oranges. So our approach is to generate top lists to propagate the frequencies using published CWE taxonomies, to publish multiple top lists at different levels of abstraction. And this analysis and these results were actually done in a previous paper published in IEEE CompSec earlier this year by us. And so we combine the improvements from that CompSec paper in data collection with the equation improvements that are in this paper, and we present to you today two lists for the 2019, the most significant software flaws. And so here we have the list for the highest level of abstraction, the pillars and classes. These are the top 20 for 2019. Our paper provides a really nice analysis of this, done by one of my co-authors, where she compares this list against the CWE Community's Top 25 list from 2019. And then also here we have a top 20 list for the lower level of abstraction, the CWEs that are, bases, variants, and compounds. And I'll just let you look at this list. And again, in the paper, we provide analysis of this. So in conclusion, just to back way out, to abstract way out, just to say that there's no ground truth here. This isn't physics. We're combining together multiple security attributes, severity and frequency, and there's no provably correct answer. However, the industry critically needs such measurements, and so we can't avoid doing them, and we need to do the best that we can do. And here we claim to be providing the most accurate measurements available for the dangerousness of software flaw types. So that's the end of the talk. On the bottom and on the side there, I put some pretty pictures from the NIST campus. That's where I work, at least pre-COVID. We're all at home now, but hoping to go back to work soon. So anyway, thank you for listening, and it's been a pleasure to present to you.